All right, welcome back everybody. Today I want to talk a little about a topic that I've been working on for a while, which is finding new junctions for transcripts in RNA. A big reason to do this is that there are likely isoforms that result in different proteins and stuff, which haven't been identified yet because either they're rare or if they are happening pretty frequently, the RNA life isn't very long, so they get degraded relatively quickly. So it makes them really hard to identify, and therefore, if they're not that common, they're not going to be in the annotation file or the GTF that we use when we're aligning to our genome. Identifying new genes can help lead to new things like relationships between that new isoform and maybe a disease that is out there. So if there's a protein that is related or correlated with a disease, identifying that transcript can be beneficial. When looking around, I wasn't able to find something that was more step-by-step on how to perform this. It was more rather, okay, with star, it gives you a junction output. Okay, what can you do with that junction output? I couldn't really find anything as to what to do next. So that's why the main motivation behind making this video is that if other people kind of are in the same boat where they want to identify new junctions or kind of analyze new junctions, hopefully this can be helpful to them. If you guys find this helpful, please hit like and subscribe. It could potentially save somebody else a lot of time in the future if they're looking to do kind of the same thing that I did here instead of having to go entirely from the beginning again. So what are we talking about when we talk about the isoforms with the gene? So if we do gene isoform, we get some really nice pictures. So for example, this guy, this gray-black bar along with the colorful bars here are the DNA, for example, in this case. And each one of these colorful bars are going to be the like the exon region that is actually getting spliced together in order to create the mRNA that the protein will get transcribed from or translated from. And so a lot of these transcripts are already in the GTF file when we downloaded it, like with the musculus. There were, it's a big file, so there's tons and tons of different transcripts for all the different genes that are more common. But if we want to identify genes that aren't in there, we have to do a little bit more work. And Star has the output of that junction file. But we can even go a little bit further and work with something called Portcullis, which is what I'm going to show today, which does a little bit more math in the background to pull out junctions that are a little bit higher confidence. But anyway, so the thing that we want to find is, okay, there's already all of these junctions that are identified in the GTF file, which is great. But we want to find potentially new junctions that, in the case of today, we have the musculus RNA sequencing file, potentially are more related to what we had done as a treatment and not necessarily in mice in general. So the GTF is probably just generic, but if we're going to irradiate the mice, like in our sequencing experiment, this might identify junctions that are particular to irradiation in either p53 knockout or p53 positive mice, that wild type. Anyway, so going on, what do we need now in order to identify these? Well, RNA is probably going to be the best way because we're going to look at the messenger RNA, which is literally the transcript for the gene. And Portcullis is a great tool, like I had mentioned, to work with these BAM files, and it stands for the portable culling of invalid splice junctions. So if there's a junction that, if we go back to that picture, is maybe at the end of the yellow, but then it's split, as you can see with the little bar. So the beginning part is at the end of the yellow, but then the second half of the read is aligning a megabase away. Based on all of the other junctions that are identified from the alignment, Portcullis looks at the confidence of that. So if there's half a read aligning to the end of the yellow and then the other one is a megabase away, how many other junctions of our mouse are that same way? If the probability is really low, Portcullis might throw that junction out because it's invalid, as it would call, invalid splice junction. Portcullis can use top hat 2, gsnap star 2, or HiSat 2. And today I'm going to use star 2. Star does give that junction file, the sj.tab, but like I had mentioned, Portcullis I think is not better, but what I have settled on for my other work. So I'm going to show that one today. Another couple files that we need are going to be something that if you've made it to this point, you're already going to have. So with the star 2, you already need the genome and the annotation file, right? So for Portcullis, we're going to need the genome file, and then in order to annotate, so that's where I'm going to use RegTools. RegTools has a function that's called Junctions Annotate, and in here we can feed in the output from Portcullis, which I'll show. If we go ls, we have Portcullis out, and in that folder there's all the different steps to the full pipeline, but then there's this junctions bed. Then we give it the genome and then the annotation, and it'll give us a really nice output to determine whether or not it's like a known junction, or how or what part of that junction is not known. So if it's a known donor, but it's not a known acceptor, that would be an unknown junction, for example. So yeah. So in order to install Portcullis, something that I want to make note of here is that I was not able to get it to work in my virtual environment, which is why right now I'm on my main computer. And then the Python versions and everything were the same, which is really frustrating. But so in order to install Portcullis, all I had to do on my main computer was conda install Portcullis, right? Because we already have bioconda channel installed. So if we run this, it'll probably tell us that the requirements are already met for it. And then the other tool, in order to install RegTools, just as easy. We can do conda install and then RegTools, and it'll be the same thing. RegTools installed in the virtual environment really easily, but Portcullis is the one that had issues, which is really frustrating. To run Portcullis, if we do Portcullis and then -- help, it gives us this really nice help down here. And generally, what I have been doing is doing the full pipeline. So it's going to be the Portcullis full, and then whatever options with your genome file, and then your BAM out. And I just ran it super generically by leaving everything at the default, but changing the number of threads. So for example, what I had run was Portcullis full, and then I changed the number of threads to 8. And then we have to feed in our genome file. So that'd be musculus DNA, primary assembly.fa, and then the BAM file. So if we scroll back up, that BAM file that I aligned was here. And this is one of the shortened ones that are on the GitHub page for the bioinformatics RNA sequencing stuff that are in the old videos. So I just downloaded this and then unzipped it, realigned it to the genome after running the star indexing stuff. So after running this, we get a really nice Portcullis output file that looks a lot like, or it is this. So here we have the junction index that it identifies as being valid. We have the chromosome, so this is chromosome 1, the length of chromosome 1, the start and the end of the junction itself, the size of the junction, and then left and right is based on the number of base pairs on each side of the junction, so actually on the exon region that the reads are. So the junction here is actually like the breaking point, and then here is the start of the read to the junction all the way over to the next junction where the exon starts to the end of the read, if that makes sense. And then there's a lot of other statistics in here too that are all on the Portcullis page that I'm not going to really go into. But something to mainly keep focus on here is going to be the suspicious. So if something is suspicious, you probably don't want to keep it. And then potentially false positive as well. So in these, if I was going to go through this file in particular for like a downstream analysis here, I would probably data filter, and then I want to remove anything in here that has a 1, and then anything in potentially false positive that has a 1 too. So now we're looking at ones that Portcullis is pretty sure is a real junction because we have removed anything that was potentially false positive. So this is the output from Portcullis, and there's other things that you can do with Portcullis. So in this case, I only ran one BAM file, but there's this other package that comes within Portcullis, or comes kind of side by side with Portcullis, called JuncTools. And in here, I've often used set. So what set does is it lets you run a bunch of Portcullis files independently. So this is on our SRR 2121-770 sample. But if you were to run it on all the different samples that we had, then you could come back later and run JuncTools set. So JuncTools set is going to let you create what I consider or call a master junction file. So if you do union, then you can have like all 12 or 16, however many files you have. You can basically merge them into one big file, and then JuncTools will kind of give you like an output statistic that looks a lot like this one, but instead of over here, there's a samples column somewhere, number of samples. Instead of having just one, then it'll tell you how many samples out of all of the ones that you feed in, for example, that have this particular junction, which is super handy to have. If you run Portcullis full on all of your BAM files at one time, it'll merge them together, which is really frustrating because then you end up with one sample and you can't really distinguish like one sample from another. You still have to rerun all of them independently to find out which junctions are in each sample. So I run them independently, get this output, and then merge them together with JuncTools, which I'm not going to show here because I only have one run, and I had to rerun them all because I zipped them up and put them on my NAS. But I only have one. Otherwise, this is really easy to do here too. So it'd be JuncTools set with these parameters if you want to do intersection, kind of like bed tools, intersection, so on and so forth. After running Portcullis and getting this really nice output, I ran RegTools. So RegTools annotate is super handy because it'll tell you which gene like this particular junction came from, and whether or not it's known with all of the other attributes. So for example, if we pull this up, it looks like almost all of ours are known, except very few. But it's a subset file too. So if we go back up, we can filter this and look at filter. Known junction, probably not going to be many. There we go. Okay. So I'll show the code that I did for that one too. So after this, you get a nice folder structure. So you end up with Portcullis out. That's just the default name. If you run like the parallel, you can change this output name with Portcullis by oops. Output, here you go. So you can give it that bracket, which will then feed it into the sample name, and it just makes it a little bit more organized. But in this case, with only one, I wasn't going to worry too much about it. But to run the JuncTool or the RegTools part, what I did in this example here was RegTools Junctions annotate. Have to remember the S here because I forgot that in Small error causes a lot of time taken. And then let's look at the help here quick. So this is super straightforward too. It's RegTools, Junctions, Annotate. And then you have two options that you can either pick or ignore. -S is going to include the single exon genes, and I included those. And then -O, lowercase o, is the file that you want to point your output to. And so when I was doing it, I did RegTools, Junctions, Annotate, then -S, so I wanted to keep those single exon genes, and then -O for lowercase o, and then I told it annotated junctions .tsv, or you could do a tab too, doesn't really matter. CSV will import into Excel, like if you double click on it, it won't look right, so either tab or TSV. And then you're left with the three options, the three files here at the end, right? So we can go portcullis out, and then 3-filt, so it's going to be the final step of portcullis full. It does 1, 2, and 3. Then from there, you want to do portcullis filtered, and we can look at all the portcullis filtered files. So in that final folder, it has basically the final run of what it's determined to be a real junction or not, and that's where we have these passes here. So these are the junctions that had passed its filtering based on that 95% intron length. So we want pass, of course, and then junctions, and then RegTools takes in the bed file, as you can see, junctions.bed. Then we need to feed in that reference. So this is going to be the same reference that you aligned your raw reads or your trimmed reads to your genome with, and that's this ref. So in this case, I did musculus dna.primary.assembly.fa, so the fasta file. And then finally, you need your annotations.gtf. So this is your transcriptome file, essentially, that has all of the different transcripts that are possible in your reference genome. So here we could do musculus, and then I did the 103 version GTF. And if you go ahead and run that, which I'm not going to do here, you get a really nice output that looks like this guy. Annotations junction TSV. So you have your junction start and your end, and then the portcullis junction name that Portcullis gave it, as well as basically the same thing that Portcullis had here with the splice site 1 and splice site 2. Basically, the exon, the last two reads, the last two base pairs of the read before the junction are GT, and then the first two of the second half that aligned was AG. So there's no acceptors skipped. There were 0 exons that were skipped. Donor skipped was 0. N, if we go to the junction or the RegTools page, N means that this exon junction is not present, so it's novel, and the transcriptome provided. So N basically means that where the read had broken, so if the read starts here and goes to here before it has to be cut and then realigned later, where it's being cut does not match with any location in the GTF file, as well as where that read starts to align again is not in that GTF file either. So that means that we have a novel junction, donor, and acceptor as entire. If we look at, let's say, NDA, then we have a novel donor acceptor combination. So the donor is known, the acceptor is known, but as you can see, if we have exon 1, 2, 3, we don't have exon 1, 3 in this transcript file on the very top. So then we have a new combination, which is really interesting too. So this is in an annotated gene. So this might be something to explore further to find out what is actually happening there. And here we have a CD84 cell gene, which is also a novel donor acceptor combination. This could be something to also explore, which is really interesting. Just kind of browsing here. Otherwise, nothing is really popping out as far as name quite. Those are the CD86, was it? Was really interesting. So, or 84. So looking further, now you'd be able to look and find out, like, potentially, is this related to whatever the treatment was for the SRR 2121-770 mouse? Is this an irradiated mouse? And if so, could this be something that is then related between all of the irradiated mice? And to do that, what you would want to look at is you could have this be your sample name and merge all of your junctions. So you have your start, end, your chromosome. Merge all of your junctions together based on your unique mapping reads. So here the file was extremely small, but you have your unique mapping reads across this junction. And then the higher amount of unique mapping reads from your multi-mapping reads, that ratio, the more likely that junction is probably real or has a little bit higher confidence. So like in this case, this is a really good junction. Let's see if we can find the rel2 raw, this guy, for the 12. So 54. Just browsing through here. So 100% of the reads are unique. Of course, with a higher read count file, I think this is only in the top 100,000 potentially reads out of the transcript, the RNA sequencing file. With more, you're obviously going to have more confidence with your particular junctions too. But yeah, so here with looking at then your unique mapping column, you could use this as like your read counts for each gene, right? So you have your start and your end. You now have them annotated. So you can say, okay, that's this gene or this transcript combination, however you want to label it. And then compare between your irradiated mice, unique mapping reads. You can compare with your P53 knockout, so on and so forth. And this could be like your raw read, not your raw read, your raw counts that you could feed into DSeq2 then, for example, to find out if there's a difference in splicing reads across this junction for P53 mice that have been irradiated, for example. But yeah, so I hope somebody finds this helpful now that this is kind of laid out. Looking back, it seems super obvious that you have Portcullis, you have all your junctions, then you need to annotate them. And how do you do that? You use junctions annotate. But it took me a lot longer than it probably should have to figure that out. So hopefully this can save somebody a lot of time in the future. So yeah, like I mentioned, if you guys find this helpful and find it interesting at least, go ahead and hit the like and subscribe button. Like I said, really hope that this saves somebody else an awful lot of time in doing this in the future. And hopefully somebody can find some unique correlating junctions too. That'd be really awesome. So yeah, thanks guys for watching. See you later.